quick synopsis. We have a ball rolling with a purely horizontal velocity off the edge of a ramp, falling 0.96 meters to the floor, landing 0.7 meters in the x direction from its initial point. We set this up as a vector equation, so everything is an I or j component or a combination thereof, and we want to be explicit about that throughout. So the initial velocity, we'll say, is just v0x times I. We could just use v0, but let's go ahead and remind ourselves that this is an x. Okay, so in the x direction. Our delta s is the vector from here to here, just boom, this vector. This is our delta s vector, 0.7 meters times I minus 0.96 meters times j. That should be very obvious. Our acceleration, while in free fall, from the instant we leave the ramp to the instant we first touch the floor, the acceleration is 9.8 meters per second squared downward, which means it's in the negative j direction. We are, of course, assuming the usual, or the most standard I, j directions. Okay, so we have these conditions. Now everything just follows from the laws. What do we know? We know that the change in the vector velocity is equal to the vector acceleration times delta t. And this would then be negative 9.8 meters per second delta t times j. That Vf is V naught plus delta V. That works for vectors as well as it does for anything else, because what does delta V mean? It means Vf minus V naught. Very obvious. V bar for uniform acceleration. If A is a uniform acceleration, it's going to be V naught plus Vf over 2, the vector equation. Both components will satisfy this, assuming uniform acceleration. And we're kind of implicitly assuming uniform acceleration up here because I just wrote A rather than A bar. If we have a variable acceleration, I'm not going to write just A. But let's be explicit about that also. Then delta S, our vector displacement, is going to be what? Our average vector velocity times delta t. Now, I haven't done this in all detail rigorously. You should think it through. But our rules for dealing with vectors are completely compatible with everything we've done here. Now, of course, Vf is V naught plus delta V, so we can replace Vf here with V naught plus delta V, but delta V is A delta T, so we have it here. And we put all this together, we have just one simple step. We got 2 V naught over 2, and then that's multiplied by delta T, so we have V naught delta T. And we have A delta T times delta T, A delta T squared over 2, 1/2 A delta T squared. All vector equations, or all vector expressions. Okay, so this works as a vector equation every bit as well as it does as a scalar equation, or as a vector equation in one dimension, which is really the way we've been using it. So we have the first equation of motion right here. The second equation of motion, well, just replace our delta V with A delta T. Third equation of motion we have. What about our fourth equation of motion? That's a little bit trickier, but just to be complete, we just dot both sides of this equation by A. Now, dotting on the right side or dotting on the left makes no difference because dot product is commutative. So we get A delta S, V naught plus Vf over 2 dot A, then times delta T. A delta T is just delta V, which is Vf minus V naught. Now, this is a dot product since this was a dot product. So we have our dot product A dot delta S equals Vf plus V naught dot Vf minus V naught. You can easily check that Vf dot Vf is just the magnitude of Vf squared. They're in the same direction. The cosine of the angle between them is 1. So when you do magnitude of this times the magnitude of that times the cosine of the angle, you just get the magnitude of this times the magnitude of that, which is Vf times Vf, or Vf squared. Same with V naught. And then your plus Vf V naught here and your minus Vf V naught here take care of each other. And you have this equation, which is just another form of the fourth equation of motion, where now your A and delta S have to be as a dot product. If you multiply this by mass, you get force dot delta S, which is work. And here, multiplying through by M, you're going to get final kinetic energy minus initial kinetic energy, the work kinetic energy theorem. So that's all worth knowing. Okay, now back to the original problem, because that's kind of a digression, but it kind of comes naturally out of what we're seeing here. We have this equation, so we write the equation again. We replace A with negative 9.8 meters per second delta T, the A delta T, with 0.9 meters per second squared delta T times J. And could have replaced V naught with V naught xi at any point, but I didn't. We get V naught delta T minus 4.9 meters per second delta T squared, and it should be V naught, well, this is still V naught delta T. Here we explicitly express this vector as a component in terms of its J component. This is equal to this. Now, if we jump over here, we have the same equation, and we replace now our V naught vector with V naught delta T, V naught x I with this. So now we have V naught delta T, V naught x delta T times I. This is the same as it was. The I component equals the I component, so V naught x delta T has to equal 0.7 meters, and the negative 4.9 meters per second times delta T squared has to equal the negative 0.96 meters. And we easily solve for delta T here and for V naught x up here.